Welcome to Chapter 5, The Role of Probability. This video content is based on Essentials of Biostatistics in Public Health by Lisa M. Sullivan. Probability is the foundation of statistical inference. In public health, we use it to understand risk, interpret diagnostic tests, and estimate how likely certain events are in a population. In this chapter, we'll explore key probability concepts and how they are used in real-world decision-making. First is sampling. We rarely collect data from an entire population. Instead, we study a sample, a smaller group, and use probability to infer what's true for the whole. This introduces the idea of sampling variability. Different samples may give different results. Probability helps us measure how likely it is that our sample reflects the truth. Now let's look at 5.1.1, Simple Random Sampling. This is the most basic probability sampling method. Everyone in the population has an equal chance of being selected. In 5.1.2 systematic sampling, we select every nth person from a list. This is easier to implement than random sampling, but still preserves randomness. Next is 5.1.3, stratified sampling, where we divide the population into subgroups or strata and then randomly sample from each. It ensures representation across key characteristics like age or gender. In 5.1.4, convenience sampling, participants are chosen based on ease of access. This is fast but not random and often leads to bias. 5.1.5, quota sampling involves selecting a fixed number from certain groups. It improves balance but lacks true randomness. Second is basic concepts of probability. Probability is the likelihood that a specific event will occur. It's always a number between 0 and 1. An event that's certain has a probability of 1. An impossible event has a probability of 0. Here are some key terms. Simple event, one specific outcome, like rolling a 3 on a die. Compound event, more than one outcome, like rolling a 3 or a 4. Mutually exclusive, two outcomes can't both happen at the same time. Complement, the probability that an event doesn't occur. We say the probability of not A equals 1 minus the probability of A. Third is conditional probability. Conditional probability asks, what is the probability of event A, given that event B has already occurred? We read this as the probability of A given B. This concept is central to screening, diagnosis, and risk evaluation. In 5.3.1, evaluating screening tests, we assess how well a test performs by understanding conditional outcomes. 5.3.2, sensitivity and specificity are key metrics. Sensitivity, the probability that a test is positive given the person has the disease. Specificity, the probability that a test is negative given the person does not have the disease. Next is 5.3.3, predictive values. Positive predictive value or PPV, the probability that someone has the disease given they tested positive. Negative predictive value or NPV, the probability that someone does not have the disease given they tested negative. These all rely on conditional probability to interpret testing accurately. Fourth is independence. Two events are independent if the outcome of one does not affect the outcome of the other. We say the probability of A and B equals the probability of A times the probability of B. This is important when combining probabilities and determining whether risk factors interact. Fifth is Bayes' theorem. Bayes' theorem allows us to update our understanding of probability with new information. It combines prior probability with conditional probability to give a new estimate. Bayes' theorem tells us that the probability of A given B equals the probability of B given A, multiplied by the probability of A divided by the probability of B. It's especially useful in clinical testing. For example, what's the chance a person actually has a disease after testing positive? Bayes' theorem reminds us that context matters. A positive result in a low prevalence setting may still have a low probability of being correct. Sixth is probability models. Probability models represent real-world uncertainty in mathematical terms. 5.6.1, binomial distribution is used when there are only two outcomes, yes or no, success or failure. It models repeated trials, like how many vaccinated people in a group of 100. 5.6.2, normal distribution is the classic bell curve. Many biological traits follow this shape. It's symmetric, centered on the mean, and widely used in inference. 5.6.3, Sampling distributions represent how a statistic, like the mean, behaves across many random samples. This concept underlies confidence intervals and hypothesis testing. Conclusion probability is the language of uncertainty. It allows us to describe, measure, and reason about what might happen and how likely it is. From simple outcomes to complex screening scenarios, probability shapes how we understand health and make decisions. This chapter introduced sampling strategies, probability rules and concepts, conditional probability, sensitivity, and predictive value, independence and Bayes' theorem, binomial, normal, and sampling distributions. These tools prepare us for the next stage, drawing inferences and making data-driven decisions. This concludes Chapter 5, the role of probability. This video content is based on Essentials of Biostatistics in Public Health by Lisa M. Sullivan.